Welcome to this work, a new training pipeline for an improved neural transducer. This is work by me, Albert Zeyer, André Merwold, Ralf Schlüter and RNNT. The motivation for this work is to have a model which allows for time-synchronous decoding, which is also important for online streaming. We generalize from the RNNT transducer RNNT model and also from the recurrent neural aligner RNA model. And we also extend from both these models to have a more powerful model. Then we also compare label topologies, meaning that for example, in CTC, you have label loop. You can repeat the label, and you have blank. In RNA, the difference is you don't have label loop. And in RNNT, the difference is this is not time synchronous anymore. Only the blank label proceeds in time. And then also we compare the difference between having an explicit blank label, like this is usually the case for these models, but we could also have this as a separate emit sigmoid probability, which states whether there's a new label or not. We compare two training criteria. First of all, full sum over all possible alignments. This is a standard RNNT loss, and also RNA uses an approximation of that. And then we can also use frame-wise cross-entropy training. And this is important to allow for more powerful models, especially our extended model needs it. And this also has other advantages. We will come to that. The setup is an end-to-end setting on subword BPE units. The experiments were done on switchboard, 300 hours. All the code and setups are published. So to generalize the label topology, first of all, let's introduce a notation. We have an input sequence x1 to t, output on our target sequence, and these are the non-blank labels y1 to n, and then the alignment labels or frames, alpha 1 to u. U can be different to t if it's not time synchronous, like in RNNT. And these alphas are also blank labels. And the blank labels, as said, you can model that as being part of the labels, one big softmax in the end, or have a separate probability to model whether you emit a non-blank label or not. And yeah, as I said, these are the labels are the 1000 PPE subword units in this work. So in the picture, I tried to visualize the label topology. Here, the label can be repeated in CTC, and then there is blank in between. This is time synchronous. Difference to RNA and also monotonic RNNT uses the same, is that you don't allow to repeat the label, and otherwise it's the same. RNNT only proceeds in time for blank and otherwise not. So in U here, in this case, is n plus t. So to come to the model, the original RNN transducer model looks like that. You have an encoder where the audio, the input gets in, and then a prediction network where the previous label, non-blank label, gets in, and also it has state. So this can remember the whole context, whole history of labels. This is very much like a language model. And also you can initialize it like that. And then this gets combined in a joint network, as a feed-forward network, and this produces probability distribution of all the output labels, including blank. When you unroll that over the alignment frames you can draw the same model as this. So here it gets from left to right, and this carries over the state. And joint network doesn't have state, and this produces the outputs. And this bold here means that this is a non-blank label, and this gets fed into the prediction network, and these are blank labels. When you come to the monotonic RNNT, it's the same model, but different label topology. This is now time synchronous, meaning that every time frame there's a new label, new output, and now this is somewhat simpler. The recurrent neural aligner is conceptually even simpler. It's just one single RNN model here, and you fed in all labels, blank or non-blank. Here, not only the non-blank labels get fed in. And when you generalize that, here time synchronous label topology, you can draw it like this. We introduce the concept of slow RNN and fast RNN. Slow RNN meaning that this runs on a slower time scale. In this case, only when there was some non-blank label which get fed in here. So this is one generalized generalization. Other is that this is now also an RNN, so you have the state dependency here, and in general we add all possible dependencies basically in this picture. Also here encoder has a dependency to the slow RNN. So encoder in our case is a B-LSTM, and we do time downsampling. The slow RNN is an LSTM, or could also, you again could restrict the context, and it's a feed-forward network. Fast RNN is an LSTM, and then on top there's some usually joint network where you combine everything, or just a joint network. To come to the definition of the probabilities, we want to define the probabilities for the output sequence, non-blank labels, and this is the sum over all possible alignments, alphas. This sum is basically defined by the label topology. And then you have the product over the use, or if this is time synchronous, this is the product over t, and then the probability per frame. And this is the most generic way to write it, including the full history. Now you can either have an explicit blank label where you have just one single softmax, big softmax, including the blank as a label, or what we use here in our work, you can have a separate emit unit which defines the probability whether there is a new label or not. So you have sigmoid for blank, basically means there's no new label, and this means there's some new label. And then you can combine it in this way. And basically, when you compare both, these are both mathematically equally powerful, just the modeling is different. And here you don't really have any explicit blank. This is just the way to write it, to formalize it. And the fast RNN and slow RNN can be formalized like this. So to come to the training, so the full sum loss, the standard loss for RNNT, is like that. You have the full sum over all possible alignments. Important here to note is that to be able to calculate this efficiently, you need to have a zero order or first order dependency on the alpha history, but no restriction on the y history. So this is the case for RNNT. It doesn't have any zero order dependency on alpha, but full history on the y. And frame-wise cross-entropy loss is simpler, but the disadvantage is you need to have some alignment. We will come to that, where you get it from. The advantage, it has multiple advantages. First of all, it's much faster in calculation, so twice as fast in our experiments for training. Then it also has, the convergence is faster and more stable, and it allows for further methods like chunked training. Chunked means that you chunk up your sequence into parts. And this makes it even faster because less zero pairing. Also, you don't need any filtering by sequence lengths. And importantly, this is very effective regularization. This is similar to truncated backpropagation. Other common methods which you can use here is label smoothing or focal loss, and also scheduled sampling and so on. And importantly, this has no restriction on the order of alpha. So this allows for more powerful models. And for our extended generalized model, this is even required, because this has full dependency on the alpha. So our training pipeline looks like that. We start from scratch with full sum training. So for some model where you can calculate this efficiently, we train for 25 epochs. Now we calculate an alignment. And now again we start from scratch for some extended model, with our extended model where full sum would not be possible anymore. And here we use cross entropy training and train for 50 epochs. So this uses the alignment before. And usually we keep the alignment fixed, so we iterate only in this last part to tune model parameters or whatever. The decoding is very simple. So we search for the best alignment sequence. This is beam search decoding with a fixed beam size of 12 hypotheses in our case. The hypotheses are the partial finished sequences alpha 1 to u. And the pruning is also based on the score for alpha 1 to u. And this is time synchronous. in case for CTC and RNA label topology, or synchronous over the alignment axis in case of RNNT. So to come to experiments, first of all, ablations and variations. This use the transducer baselines V1 and V2. These are extended models. We never use an external language model in our work here. This has full label context, alpha and y, and these are LSTMs. And we use separate emit sigmoid, so no explicit blank. The baseline are like these, B2 is slightly better. First experiment is no chunked trainings, and this gets much worse, so we see that chunked training is quite important. Slow RNN always updated, meaning it behaves like fast RNN, it's not slow. Also gets worse, so this shows that this concept of slowness seems to be helpful. You can also remove it completely, the slow RNN, so then basically you have the RNA model. And this is very similar here to this line. Difference is this has a bit less parameters. And then you can also remove the encoder feedback to the slow RNN. This is the case like in RNNT, and again you lose a bit. Or you can also, in addition, remove the alpha label feedback to fast RNN, again like in the case of RNNT. Here it gets worse. Here it's the same, so it's a bit unclear. But when you completely remove the fast N, so basically you just have a joint network, feed-forward network, then you really have exactly the RNNT model now here in this column, and it gets much worse again. Also here the comparison of having this explicit blank or versus no separate like in the baseline, and the explicit blank also gets worse. So this seems to be helpful to have this separate emit. Another important experiment is to vary the sequence length. We know from literature that the standard global soft attention encoder-decoder model has problems to generalize on longer sequences. To test this, we concatenate every capital C consecutive sequences from our eval set, meaning that the sequences get longer. In this case, up to 290 seconds is the average sequence length here, and we see that the attention model basically fails to operate here. And for the transducer model, we see that it gets slightly worse, but still performs okay on these long sequences. To come to the overall comparison, attention versus transducer model, we see that the transducer model is better than the attention model. And also when compared to the literature, one interesting observation which we made is that the number of training epochs here is very important and seems to correlate a lot with the final word error rate. The best, basically, the longest trained is also the best here in this table. And our results seems to be similar to other models trained for similar time. To come to the conclusion, we generalized and also we extended from the RNNT and RNA model, and our extended and generalized model performs better. We also compared the label topologies. Here the conclusion is no label loop seems to be better, like in case of RNA or RNNT. And then frame-wise cross entropy, it had many advantages. First of all, it is a requirement for our generalized extended model. Also, it was much faster to train, and also conversion was faster and more stable. And also then important are methods like chunk training, which made it much better and also faster. And next is the comparison to attention-based models. We saw that our transducer is better than our attention model. And this is in contrast to other literature results, which usually show that attention model is better than transducer. But in our case, we have our extended, improved transducer and also the better training. And then also our transducer generalized to longer sequences. Side observation from literature review is that the total number of training epochs correlates strongly with word error rate. And remark on that is that the amount of computation effort is in the end important. Frame-wise cross entropy is crucial also here in this respect. Thank you for your attention. Here are some appendix backup slides.